Right now, somewhere in your city, a truck is making its rounds. You've probably seen it dozens of times, heard the groan of its engine, caught a whiff of something unpleasant, and kept walking without giving it a second thought. Most people don't. Most people assume the garbage truck just picks things up, drives them somewhere far away, and that's the end of the story. Out of sight, out of mind. But that assumption is dangerously wrong. What actually happens inside a garbage truck from the moment your bag hits the hopper to the final destination miles away is one of the most overlooked industrial processes happening right outside your front door every single day. There is pressure inside those metal walls powerful enough to crush a car engine flat. There are chemical reactions that generate heat without any flame. There are gases accumulating in spaces where a single spark could cause an explosion. And buried somewhere in that compacted mass of waste is a tiny object, something you've probably thrown away yourself without a second thought, that has already caused millions of dollars in damage worldwide and is responsible for one of the fastest growing hazards in the entire waste management industry. By the time you finish watching this, you're going to look at every garbage truck that passes your home in a completely different way. And you're definitely going to think twice the next time you drop a dead phone or old vape pen into your kitchen trash can. Let's start from the very beginning, not with the dramatic chemistry or the fires. We'll get there, but with the sheer scale of what we're talking about. Every single morning, in cities and suburbs and small towns all across the world, an enormous, invisible fleet rolls out before most people are even awake. In the United States alone, over 100,000 garbage trucks are in active operation on any given day. Globally, the number of these vehicles in daily circulation is estimated at around 500,000. These aren't just trucks. They are the circulatory system of modern civilization. Without them, cities would become uninhabitable within days. Waste would pile up in streets, in courtyards in front of homes and hospitals and restaurants. These siase would follow. Every single convenience of modern urban life depends, at its foundation, on this fleet that most people actively ignore. A single garbage truck operating on a standard urban route will stop somewhere between 300 and 1,000 times in one working day. Think about that. Every few minutes, another stop, another load. The driver and crew move with practiced efficiency, and the truck's mechanical systems do the real heavy lifting. Literally, but not all garbage trucks are the same. And understanding the difference is important before we get into what actually happens. Inside, there are 3 primary types in use around the world, and each one approaches the problem of waste collection differently. The most common type, the one you're most likely to see in a residential neighborhood, is the rear. This is the classic design. A large rectangular hopper, opening at the back where workers feed bags, bins, and loose garbage. Once enough material is loaded into the receiving area, the mechanical system takes over and pulls everything inward. It's straightforward, reliable, and extraordinarily effective. The second type is the side loader, which has become increasingly common in areas where labor costs are high or routes are particularly long. These trucks are often operated by a single person. A hydraulic arm extends from the side of the vehicle, clamps onto a wheeled bin sitting at the curb, lifts it high into the air, and tips the contents directly into the truck's body. The driver never has to leave the cab. The whole process can take under 30 seconds per stop. The third type is the front loader, designed not for residential streets but for commercial sites, shopping centers, factories, office parks. These trucks have 2 large forks at the front that slide beneath a dumpster, lift it completely off the ground, arc it up and over the cab, and dump the entire contents into the open top of the vehicle's storage body. It's an impressive piece of engineering, and for high-volume commercial waste, it's unmatched in efficiency. Now, a standard rear-loading garbage truck has a storage body with a volume of roughly 20 to 35 cubic meters. For reference, that's approximately the same volume as an average 1-bedroom apartment. If you just threw trash into that space loosely and let it pile up, you'd fill it quickly and make very few stops. The truck would be constantly driving back and forth to dump sites. That would be economically and practically useless. So instead, every garbage truck contains what is arguably its most important component, the compactor. This is where things start getting genuinely fascinating. The compaction mechanism inside a garbage truck is, in its essence, a hydraulically powered press. But calling it just a press is like calling the engine of a Boeing 747 a fan. The forces involved are extraordinary. Picture the most powerful industrial paper compactor you've ever seen. Now multiply its force by that begins to approximate what's happening inside the body of the truck every 20 to 30 seconds. Here's the specific sequence of events. When the hopper at the rear fills with garbage, a large steel plate called the packer blade, sometimes referred to as the sweep panel, is activated by the hydraulic system. This plate first moves downward and then forward in a sweeping motion, capturing the loose material from the receiving hopper and pushing it into the main storage chamber. Then the plate delivers a second, more forceful stroke. This second stroke is the one that does the real work. It rams the material already in the chamber with additional force, compressing everything that came before it even tighter. The hydraulic system driving this mechanism operates at pressures of approximately 190 atmospheres. To give you a frame of reference, that actually means something that is roughly equivalent to the water pressure you would experience nearly 2 kilometers below the ocean surface. It is the kind of pressure that does not bend or deform objects. It obliterates them. Under 190 atmospheres of pressure, a plastic water bottle does not crinkle. It shatters into fragments and becomes part of a compressed mass, indistinguishable from everything around it. Cardboard boxers, double-walled reinforced, designed to protect fragile items during shipping, are reduced to thin sheets, almost like cardboard paper. Aluminum cans that are engineered to withstand significant internal pressure are pancaked flat, thinner than a coin. Glass, which under normal circumstances breaks into jagged shards, fractures into a fine granular mixture that blends into the surrounding compressed waste. The result of all this compaction is remarkable efficiency. The same volume of garbage that would fill an entire apartment is reduced to roughly 1/5 or 1/6 its original size. This is how a single garbage truck can collect between 10 and 15 tons of waste on a single shift without stopping to unload. By the end of the working day, the storage body doesn't contain loose garbage anymore. It contains a dense, compressed monolith, a solid mass of waste so tightly packed that when it's eventually ejected at the dump site, it comes out not as a cascade of individual items, but as a single, roughly unified block that holds its shape for a moment before slowly breaking apart. But here is where the story takes a turn that most people have never considered. Compaction is only the beginning of what happens inside a garbage truck during a normal working day. Because once that first load is compressed and the truck begins rolling toward its next stop, something else starts. Something that truck manufacturers don't exactly advertise on their spec sheets. Think about what you've just assembled inside that sealed metal chamber. You have organic food waste, vegetable peelings, leftover meat, used coffee grounds, soggy bread, fruit that went bad before anyone got to it. You have wet paper and cardboard. You have plastic bags that were holding liquids before they were thrown away. You have cleaning product containers with residue still inside. You have personal care products. You have anything and everything that a household produces in a day. Now you've compressed all of that together with several hundred atmospheres of pressure. You've squeezed out every pocket of air. You've forced materials that would never come into contact under normal circumstances to merge into a single dense mass. And you've sealed it inside a metal container that will be sitting in sunlight for the next several hours. The first thing that happens is heating, and not from any external source. The act of mechanical compression itself generates heat. This is basic physics. When you rapidly compress any material, the molecules within it are forced into closer proximity and their kinetic energy increases, which means their temperature increases. You can feel this yourself if you rapidly compress a bicycle pump while covering the nozzle. The metal gets warm. Now apply that principle to 15 tons of compressed garbage. Simultaneously, the organic material in that mass begins to undergo accelerated decomposition. Bacteria that are always present in food waste become significantly more active when density increases and air is removed. In fact, the anaerobic conditions, meaning the absence of oxygen that the compaction creates, are precisely the conditions under which the most heat-generating decomposition reactions take place. The bacteria are not slowing down because they've been squeezed. They're speeding up. The combined result of mechanical compression, heat, and bacterial decomposition can raise the internal temperature of the waste mass 2 or even higher degrees Celsius without any fire, without any external heat source. with nothing more than physics and biology doing their work inside a rolling metal box on a public street. And as the temperature rises and the organic material breaks down, gases are produced. Methane is generated by anaerobic bacteria processing the organic waste. Ammonia is released from the decomposition of proteins, the meat, the dairy, the various nitrogen containing compounds and household garbage. Hydrogen sulfide is produced as bacteria break down sulfur-containing organic molecules. And this is the gas responsible for the characteristic smell that hits you when a garbage truck passes close by. That distinctly unpleasant, rotten egg odor that most people try to avoid breathing. In low concentrations and dispersed into open air, these gases are offensive, but harmless. But inside the sealed storage body of a compactor truck, they accumulate. They fill whatever small pockets of space remain in the compressed mass. They concentrate. And if a source of ignition were introduced into that environment, a spark, a flame, an electrochemical reaction, the results could be catastrophic. There's also a liquid component to this story that often goes unnoticed. When you apply enormous compressive force to a mass that contains food scraps, wet bags, liquid-containing containers, and moist organic material, you squeeze out liquid the same way you'd wring water from a wet cloth. This liquid, called leachate, drips down through the compressed waste and pools at the bottom of the storage chamber. Modern garbage trucks are designed with sealed tanks to capture this leachate and prevent it from dripping onto the road as the truck drives. But that leachate is not water. It is a chemically complex mixture containing organic acids from decomposing food, fatty compounds, residues from cleaning products and detergents, and whatever else dissolved into the liquid as it percolated through the waste. It is corrosive, toxic, and has to be disposed of carefully. It is not something you want seeping into groundwater, which is precisely why it must be collected and treated. So by the midpoint of a typical working shift, the interior of a garbage truck storage body is not what most people imagine. It is a hot, gas-saturated, liquid-producing, biochemically active compressed mass, a sealed environment where complex and sometimes dangerous chemistry is happening. Continuously, invisibly, one block from where children are playing. And then we come to the element that has transformed this already complex situation into something genuinely dangerous on a large scale. Something that has forced the waste management industry to fundamentally rethink how it handles the waste stream. Something that every single person reading this has almost certainly contributed to, probably multiple times: the lithium-ion battery. It weighs a few grams. It's often not much larger than a stick of gum. It sits inside your old smartphone, inside the vape device you finished and tossed, inside the wireless earbuds that stopped holding a charge, inside the electric toothbrush handle, inside the cordless vacuum that finally gave up. When these devices stop working, or when you upgrade to something newer, the natural, instinctive thing to do is exactly what you do with every other piece of garbage. You throw it away, into the regular trash, into the kitchen bin, or the recycling bag, and that bag goes out with everything else on collection day. This is one of the most dangerous mistakes that hundreds of millions of people make every single year. Here's what happens to that battery once it's in the garbage truck. The bag it was in gets thrown into the hopper. The sweep panel activates. The compaction cycle begins, and the battery, which was designed to be charged and discharged under controlled conditions, which was designed to be kept at regulated temperatures and handled gently, suddenly subjected to pressures approaching 190 atmospheres. Inside a lithium-ion battery, there is an extremely thin membrane called a separator. This membrane sits between the positive electrode and the negative electrode and keeps them from making physical contact with each other. Under normal operating conditions, this separator does its job flawlessly, but it was not designed to survive the inside of a garbage truck compactor. The separator is thinner than a single human hair. When the compactor applies force to the battery, the separator ruptures. The moment this separator fails, the positive and negative electrodes come into contact, and at that moment, a process begins that the industry calls thermal runaway, a term that does not adequately convey how terrifying the phenomenon actually is. Thermal runaway is a self-accelerating chain reaction. The initial contact between the electrodes generates heat. That heat damages additional internal layers of the battery. The damage to those layers generates more heat. That additional heat damages more layers still. At each step, the reaction accelerates. The temperature inside the battery rises not gradually but explosively, climbing to several hundred degrees Celsius in a matter of seconds. When the lithium compounds inside the battery reach sufficient temperature and come into contact with oxygen, even the trace amounts present in the compressed waste, they ignite, and the fire that results is not the slow, smoldering kind that gives you time to react. It is sudden and violent. People who have witnessed lithium battery ignitions in enclosed spaces have described them as resembling a miniature volcano, an abrupt, intensely bright eruption of flame and sparks. What makes this particularly terrifying in the context of a garbage truck is that you now have an intensely burning lithium fire inside a compressed, chemically complex, gas-saturated mass of garbage inside a sealed metal container, inside a vehicle driving through a residential neighborhood. And the conventional response to fire, water, makes lithium fires worse. Water reacts with burning lithium compounds in a way that accelerates rather than suppresses the combustion. The fire departments who have responded to garbage truck fires involving lithium batteries describe the experience as dealing with something that seems almost designed to be impossible to fight. You cannot reach the burning material because it is buried deep in compacted waste. You cannot use water because that intensifies the reaction, and the gases produced by the burning lithium create additional hazards for anyone nearby. These incidents are not rare. They are not edge cases. They are happening every day in cities around the world with increasing frequency. In January of 2026, a garbage truck caught fire mid-route in an American city, with the source eventually traced to a vape pen containing a lithium-ion battery in Massachusetts. In April of 2025, an entire truck carrying recyclable material had to make an emergency stop on the side of a highway, where its contents were unloaded and extinguished using heavy road equipment because the fire could not be controlled any other way. In New York City, dozens of similar incidents were recorded in waste trucks and sorting facilities in the span of a single year. Industry associations for waste management in the United States document hundreds of these incidents annually. They are not exceptional events anymore. They are a systemic and growing problem. Waste management companies in Germany have reported that fires at sorting and recycling facilities have multiplied many times over during the past decade, and in the vast majority of investigated cases, the source was a lithium-ion battery found in household waste. In the United Kingdom, between 2023 and 2024 alone, hundreds of battery-related fires occurred at recycling and waste processing installations in Australia. The problem reached a scale that prompted a government-backed national public awareness campaign with a single, direct message: batteries do not belong in regular trash. A single lithium battery fire at a recycling facility in California in 2016, triggered by one battery falling into an industrial shredder, burned for several hours and caused damage valued at $8.5 million. One battery, one fire, $8.5 million. And that was almost a decade ago, when the number of lithium battery-powered devices in circulation was a fraction of what it is today. The scale of the problem in terms of raw numbers is staggering. In the United States alone, experts in waste management estimate that hundreds of millions of lithium-ion batteries end up in regular household garbage every year. In Europe, the figures are comparable, in countries where recycling infrastructure and public awareness are still developing. The situation is often worse, and the total number of lithium battery-powered consumer devices sold worldwide continues to grow year after year. Smartphones, wireless headphones, e-cigarettes, electric toothbrushes, scooters, power tools, children's toys, smartwatches, portable speakers. Each of these devices contains a battery that will eventually reach the end of its useful life. And each of those batteries, if disposed of incorrectly, is a potential ignition source inside a machine that is specifically designed to generate heat and pressure. Sensors that monitor the internal temperature of the waste continuously and alert the driver the moment it exceeds a critical threshold, typically around 200 degrees Celsius. When the alarm sounds, the driver is required to stop immediately and call for assistance. Some newer truck models incorporate. A number of large waste management companies have assigned trained personnel specifically to visually inspect the contents of containers before loading, looking for devices or batteries that should not be entering the collection stream. But all of these measures address symptoms, rather than causes. The thermal camera helps detect a fire after it is started. The visual inspection catches some batteries, but not all. The suppression system may contain a fire but cannot prevent it. The only intervention that actually prevents the problem at its source is proper battery disposal, and that requires the person standing at the kitchen counter, holding a dead phone or a finished vape, to make a different decision. The good news is that the infrastructure for making that different decision exists and is growing. Battery drop-off points, dedicated collection containers, specifically for batteries, phones, and small electronics, are now available at most major retailers, shopping centers, and in many municipalities, at designated collection points throughout residential areas. In most European countries, proper battery disposal infrastructure is mandated by law. Regulations adopted by the European Union require manufacturers to create and fund battery return and recycling systems. And since 2024, European requirements governing battery end-of-life management have become among the strictest anywhere in the world. The message in these regulations is clear. The responsibility for what happens to these batteries does not end at the point of sale. And the reason that responsibility matters goes beyond preventing truck fires. As serious as those fires are, the materials inside lithium-ion batteries, lithium, cobalt, nickel, and various other metals, are genuinely valuable resources. Lithium, in particular, is a finite mineral with significant and growing industrial importance. The global demand for lithium is being driven not just by consumer electronics, but by the vast expansion of electric vehicle production and grid-scale energy storage. The world's lithium reserves are not unlimited. Every battery that is thrown into a landfill or destroyed in a compactor fire is a battery whose lithium and cobalt and nickel will never be recovered. Every battery that is properly recycled returns those materials to the production stream, where they can be used to make new batteries. This is not primarily an argument about recycling sentiment or environmental consciousness. It is an argument about material economics. Recycled lithium is lithium that does not need to be mined. Recycled cobalt is cobalt that does not need to be extracted from mines in geopolitically complex regions. The recycling of battery materials is, at its core, a strategic industrial priority. And it begins with the decision. The process that begins when your trash is finally deposited at its destination is in some ways even more significant. It just unfolds on a much longer timescale. When a fully loaded garbage truck reaches the end of its route, it is carrying between 20 and 30 tons of material. The discharge mechanism varies by vehicle type. On a rear-loading compactor, the rear gate opens and a large internal push-out plate advances forward through the storage body, ejecting the compressed waste in a cohesive mass. It doesn't tumble out like loose garbage. It slides out as a compressed block. The individual items so thoroughly fused by the compaction process that the mass holds together momentarily before settling at large waste processing facilities. This incoming material first passes through a sorting stage, a combination of machinery and human workers who identify and separate recoverable materials. Metals are pulled out by electromagnetic separation. Optical sorters scan passing material and identify different types of plastic by their light-reflective properties. Workers at manual sorting stations catch items. The automated systems miss glass, certain grades of cardboard, specific plastics. All of these are diverted from the general waste stream and sent to recyclers. But a significant portion of household mixed waste, particularly the organically contaminated mixed material that makes up the majority of what most people throw away, bypasses or passes through sorting and goes directly to a landfill. And here is where a completely different, multi-decade process begins. At a modern sanitary landfill, the arriving waste is not simply piled up and left. Enormous machines layer and compact the material, depositing it in structured horizontal lifts and covering each layer with soil. The landfill is engineered as a system, a managed structure with built-in drainage, gas collection, and liner systems that are designed to contain what the waste produces as it sits there over years and decades. Because the waste does produce things, long after it has left your home, long after the truck has moved on to the next street, long after the sorting facility has processed and dispatched what it could. Your garbage continues to be chemically and biologically active. In the anaerobic oxygen-free conditions, that develop deep inside a landfill. Bacteria process the organic material in the waste through a different metabolic pathway than they would use in the open air. Instead of producing primarily carbon dioxide, as aerobic decomposition does, these anaerobic bacteria produce methane. Large quantities of methane. The same methane that is the primary component of natural gas. The same methane used in gas stoves and home heating systems. A mature landfill, one that has been receiving waste for years, generates landfill gas that is composed of between 45 and 60% methane, with the remainder being carbon dioxide, ammonia, hydrogen sulfide, and various trace compounds. And this gas production does not stop when a landfill is closed. It continues for decades. In some documented cases, significant landfill gas generation has been measured more than 50 years after a site stopped accepting new waste. Modern engineered landfills address this with networks of perforated collection pipes installed throughout the waste mass. Vertical and horizontal wells that capture the rising methane and channel it to processing equipment. That gas is then used to generate electricity. It is, quite literally, a power plant running on garbage. The organic matter that people threw away is being converted, years later, into energy that powers homes and businesses. But at older sites, or at landfills, in regions without the resources for proper gas capture infrastructure, that methane is simply released into the atmosphere, or parre. When concentrations build sufficiently near the surface, it ignites spontaneously. The ghostly blue flames sometimes visible over landfills at night are not atmospheric tricks or urban legends. They are burning methane. Large landfill operations maintained firefighting and monitoring equipment on standby around the clock precisely because of this risk. Alongside the gas, there is also the leachate problem, the same liquid from waste phenomena we encountered inside. The garbage truck, now happening at a vastly larger scale. Rainwater percolates down through the layers of waste, absorbing dissolved compounds as it goes. What emerges at the bottom of the waste mass is a complex liquid containing heavy metals, leached from electronic waste and batteries, organic acids from decomposing food, residues of pharmaceuticals that were thrown away, fragments of cleaning products and pesticides and personal care items. Left unmanaged, this leachate would migrate downward through the soil and contaminate the aquifers that supply drinking water to communities sometimes miles from the landfill itself. Modern landfills address this with composite liner systems, layers of engineered clay and specialized geomembrane, materials installed at the base and sides of the waste mass, combined with collection drainage systems that capture the leachate before it can escape and channel it to treatment facilities. But these systems require maintenance, monitoring, and eventual replacement. They are not permanent solutions. They are management strategies that kick the true long-term problem into the future. This is the full journey, from your kitchen bin to the hopper, to the hydraulic compactor, to the compacted mass, to the sorting facility, to the landfill, to the slow, multi-decade process of decomposition, gas generation, and leachate production. What feels, from your side of the garbage bag, like a single simple act, throwing something away, sets in motion a chain of events involving enormous machines, complex chemistry, industrial infrastructure, environmental management, and very real ongoing consequences. The machine that collects your trash every week is not a simple container on wheels. It is a compactor, a chemical reactor, and a potential incendiary device all in one. The pressure inside it can flatten metal. The temperature inside it can rise significantly without any external heat source. The gases inside it can reach dangerous concentrations and tucked into the mass of ordinary garbage. Inside nearly every truck in operation today are devices containing batteries that can, under exactly the conditions those trucks are designed to create, trigger a fire that water cannot extinguish. Every city in the world has rules about battery disposal. Every waste management authority makes the same request. Battery drop-off points exist in more places than most people realize. At electronic stores, at supermarkets, at pharmacies, at community collection points. The act of separating a dead battery from your regular trash takes approximately 10 seconds and requires nothing more than placing it in a separate bag or container until you pass a drop-off point. The next time a garbage truck goes past your home, you can look at it differently now. You know what's happening inside. You know about the compaction cycle and the pressure and the heat and the gases. You know about the leachate and what it contains. You know about the battery fires and why they happen and what it takes to stop them. And the next time you're holding a dead phone, a finished vape pen, an old set of wireless earbuds, or any small device that contains a rechargeable battery, you now know exactly what you're putting into motion if you drop it into the regular trash. You know where it goes. You know what happens to it on the way. And you know how to make a different choice.